Okay. Yeah. So, well, I'm planning to give some quickly review on what have been the developments of or regarding this topic, regarding the generation of cosmological gravitational waves that have been done during the last few years. Since I see that Axel is back and people from the steering committee. So I will be giving an overview. I hope that around the first half an hour, more or less, will be giving a state of the art and the different results that have been obtained by different people within the pencil code community. And then we'll leave some half hour at the end of the hour for some discussion. In particular, we were discussing with Axel a specific topic that we would like to discuss more regarding the numerics of the gravitational wave equation that I will introduce in a moment. So as you can see, it's quite extensive literature on the generation of gravitational waves that has been done since 2018, when we developed the gravitational wave module within the pencil code, and we started running simulations for this type of applications. So the contributors, the pencil code, and then the collaborators have been leading these publications, and also from them and from other people. So I'll give now an overview. So some of the slides are slightly repeated from yesterday's talk, and since there were also some questions regarding this, I thought it might be good. And please interrupt me any moment. I would like this to be kind of more dynamical presentation than just me giving the update. If you have any questions, or if you want to also say something about some results that you know about this gravitational wave production. So as I was explaining yesterday, we have different sources in the early universe. So we have phase transitions, and we have been studying the electroweak phase transitions in these two publications because they might be relevant for detectability of such signals using space-based detectors, as for example LISA, and also from the quantum chromodynamic phase transition, also in these publications, where we are interested in what will be the final spectrum around the nanohertz frequencies, which are relevant for pulsar dynamic arrays. This is what I was discussing yesterday. And there's also some people that have been working, and this is Ramkishore Sharma is the expert on this part. So that there have been some production of gravitational waves and of magnetic fields and gravitational waves from inflation, and they can depending on what is the end of reheating temperature when inflation ends. This can be also this can be giving a gravitational wave spectrum at different frequencies depending on this specific reheating temperature. As well, if we go beyond the slow roll inflation model, which is kind of the simplest model for inflation, we can also have a blue tilted gravitational spectrum, and therefore, if we have a scale invariant gravitational spectrum, this could be visible in many decades in frequency. So it could be actually potentially observable by different detectors. So so we have different sources of magnetohydrodynamic turbulence in the early universe. This I was also introducing yesterday. So we can have hydrodynamic turbulence or either primordial magnetic fields. And again, most of the works using the pencil code have been focusing on primordial magnetic fields. And so I will also mostly be talking about that, although there are some results regarding hydrodynamic turbulence also in this direction. So we might have hydrodynamic turbulence produced from phase transitions, as well as we can have primordial magnetic fields either from phase transitions or produced during inflation. And this will develop into a MHD turbulence. So we expect MHD turbulence to be in the end the main dynamical determining the main dynamical evolution of the magnetic and velocity fields, and therefore having a big impact on the spectral shape of the resulting gravitational wave background from these cosmological sources. So again, I presented this yesterday. So we have the different frequencies at which we can have gravitational waves, and there are different detectors. So depending on which phase transition, depending on what is the end of reheating temperature, we might have a gravitational wave background that is peaking around different frequencies. So we are interested in studying this in the full range of frequencies, and therefore then connect the results to like the different potential observations by different gravitational wave detectors. So I was showing yesterday from phase transitions, we might have detectable signals around the nanohertz frequencies for QCD phase transition, around millihertz for electrowave phase transitions, and around thousands of hertz if we have more exotic, very high temperature phase transitions. And we have, sorry, I didn't include that, but we have an inflation generated gravitational wave background. We might have something that is approximately scale invariant according to the slow roll model. So it could be detectable or not. But if we have some beyond slow roll model of inflation, we might have something that is slightly blue tilted, and that can actually then be observable by different detectors. And what I think that the work that have been mostly focusing is on kind of very low end of reheating temperatures, so temperatures around the QCD and slightly larger, and those can also be giving, sorry, and those can be giving similar gravitational wave backgrounds to this, and I'll show some results on those that could also be then potentially observable by pulsar timing arrays or by LISA, etc. So we have different ways of solving for these for these gravitational wave backgrounds, and this has been some the developments that have been done in the pencil code. So on one hand, we want to study the dynamical evolution of the magnetohydrodynamic fields, of the electromagnetic fields, and of the velocity fields of the plasma. And in order to do that, what I was presenting yesterday is when we have the MHD evolution, which has been adapted to radiation-dominated era, where these phase transitions are occurring. And in addition, this can also include the chiral magnetic potential, as Jennifer was also presenting in previous presentation. So if we include this effect, then this is also relevant and has been done within the pencil code. And on the other hand, when we're interested in inflation, what has been done by Rankishore and Axel and Newton, it's to study the vacuum Maxwell equations. And I will show how these look like and how they are being solved in the pencil code. And therefore, these are solved until the end of reheating. And then at the end of reheating is when we enter the radiation-dominated era. So then we go again into the MHD equations to evolve the magnetic fields and the plasma fields after the universe has gone into the radiation-dominated era. So on one hand, we have the dynamical equations for MHD fields. On the other hand, we have the gravitational wave equation, which I presented yesterday for GR linearized theory, which is what has been used in most of these results. But there has been some extensions of this equation that have been done mostly led by Yu Donghe, by Axel's PhD student, and they have some works on this where they are extending this to include massive gravitons, for example. So you have an additional term in your gravitational wave equation. And we have also been doing some efforts into adding some nonlinear terms in the gravitational wave equation, which will be subdominant, but might in principle have some effects on the final results. So yeah, so let me now go into the MHD description, and maybe I will repeat this since yesterday we also had some questions about these specific equations. But so when we're solving the MHD equations in the radiation-dominated era, we solve this for relativistic MHD equations. We use an ultra-relativistic equation of state for the pressure, so that the pressure and the energy density are related just by with a sound speed of 1/3 with respect to the speed of light. And we're solving in the expansion universe, which is the solution of GR for an isotropic and homogeneous universe, where it is modeled by the scale factor in the case of a flat expanding universe. So we are solving the MHD equations above this metric tensor. However, and as Jennifer was actually explaining in her presentation, oh, sorry, well, this is 2 slides. I'll go back to that one. However, even if we have this expanding universe and we actually have to take the conformal derivative of the stress energy tensor to develop the MHD equations, when the universe is dominated by radiation, then these equations are conformally flat. So we can use a rescaling of the variables with the scale factors such that these become more like MHD equations, so that we don't have any explicit appearance of the scale factor. And this was like previous work by Axel from 1996. And therefore we can just solve the MHD equation. So we have a cubic domain, which is not expanding, it's just the cubic domain, and the coordinates are actually co-moving. So then when we want to actually take the physical variables out of the solution from the pencil code, then is when we do all the rescaling as well as for the dynamical fields. So just going back to this stress energy tensor, we have contributions from fluid motions, contributions from magnetic fields, and also, yes, and that's it. So we have these contributions, and then we can derive the conservation laws. And this stress energy tensor is what then is actually sourcing the gravitational waves. So if we want to include the chiral magnetic effect, as Jennifer was showing, then we have an additional current density that comes from the chiral anomaly, and then we also have an additional evolution equation for the chiral chemical potential, which is then coupled to the induction equation and can actually produce these magnetic fields, which was extensively shown by Jennifer. So a relevant part of these results, and this is not that much connected with gravitational waves, but I thought that it's interesting since most of the people are working gravitational waves. We are interested in primordial magnetic fields. So when we have a primordial magnetic field produced at any of these phase transitions, then this will evolve until recombination. And this was also explained by Jennifer, so I will very quickly mention it. And after recombination, this becomes frozen in the plasma, and then it just expands with the expansion of the universe. So therefore, this part highly depends on what is the fractional helicity of the magnetic field. So in this case, we have a magnetic field that starts at the electroweak phase transition. It develops, it falls with MHD turbulence decay until some characteristic length and characteristic amplitude that we can put some constraints on them from observations of laser spectra by the Fermi collaboration. And here I have another plot on that. So this is the lower limit. We also have like upper limits from Faraday rotation. These are some observations from ultra high energy cosmic rays, and some constraints from CMB observations. So therefore, if we have something that is produced at the electroweak phase transition and that is potentially observable by LISA, it has to be within these constraints in order to be observable for LISA. And then it will evolve depending if it's helical or non-helical down to recombination, and potentially then it has to then be compatible with these lower limit constraints by the Fermi collaboration as well as the high limit constraints. And the same happens if we have a magnetic field that is produced during QCD phase transition. It should evolve. In this case, this is for a non-helical field, but you might also have helical fields in both cases, and therefore they will be slightly different. And also in this regard, it's important that the chiral magnetic effects, since Jennifer was explaining, the fact that we have the chemical potential makes helicity not to be conserved on its own, but it needs to be conserved with the chiral helicity, and therefore might modify the dynamical evolution of these magnetic fields. So going back to gravitational waves, and again, this is the slide from yesterday with slight modifications and additions. So what we're solving in the pencil code is the tensor mode perturbations above the isotropic and homogeneous metric tensor given by the Friedmann-Lemaitre-Robertson-Walker model. And when we derive the linearized gravitational wave equation, we obtain these terms. Here I have added an additional term that comes if we consider that the gravitons are half mass, which is what I was saying that it has been studied in this paper by Yutong and by Axel. And if we also have this term that is the second derivative with respect to conformal time of the scale factor. Again, also in this equation, we are rescaling the variables. So we are taking A times Hij, this the tensor mode perturbations above the background metric. And we're also taking co-moving spatial coordinates and conformal time, as well as co-moving stress energy tensor. And This term is exactly 0 when we're in the radiation-dominated era, because the scale factor evolves linearly with conformal time during the radiation-dominated epoch. However, when we're considering reheating, then this is not exactly equal to 0, and this was also implemented and studied by Ramkishore, Axel, and Newton within the pencil code. So therefore, we need to adapt this term when we're considering different epochs. So we have at the end of reheating, this term will appear. If we are studying the dynamical evolution of gravitational waves during a radiation-dominated era, then this term is 0, and it does not appear. And this 1 divided by the scale factor appears always, and gives a dilution with like 1 divided by t in the case of radiation-dominated era, and slightly different. I don't have now a specific evolution of A, but slightly different when we have reheating there, which is dominated by matter at that moment. So if we want to go, this was a first attempt to go into nonlinear GR that we did with Yudong and Axel also. So we added the effective stress energy produced by gravitational waves. So we have a gravitational wave. This is at the same time carving space-time, which carries also some energy density, and this energy density can lead to also an additional perturbation of the metric tensor. This is a first-order nonlinear terms. Things become a bit more complicated. There is the need to do actually more modifications to this equation, but a first attempt was done in this paper, including just one of these additional terms. So this was also implemented in the pencil code and is now available, and a current work in progress topic. So if we have this equation, we can normalize it, and this is the final equation that we're currently solving within the pencil code. So again, all these variables are normalized, they are non-dimensional, and they are co-moving. So we can then adapt the solutions from the pencil code to the different epochs, rescaling just with the temperature scale, as long as we are staying only in radiation dominated or only during reheating. And in order to solve this equation, and this was the first presentation I gave in the pencil code user meeting back in Boulder in 2018, when I was doing my PhD with Axel. So we were studying how to solve this gravitational wave equation. And initially, as you know, pencil code is a high-order finite difference, uses a high-order finite difference method, and also a third-order Runge-Kutta time integration, which, I mean, this is can be adapted, but we try to implement third-order time integration using Runge-Kutta solver and following this description. So this was our first attempt on how to solve the gravitational wave equation, just applying finite differences and evolving with time. However, we found that this was leading to numerical accuracy problems. So if we were only considering the CFL condition from the MHD solution, so we were seeing that actually for different current numbers, this is the spectrum of gravitational waves compared to the spectrum of the magnetic field, for example, and using different current numbers. So we can see that for the magnetic field, even if we go to smaller and smaller time steps, the solution is already obtained with enough accuracy. However, the gravitational wave spectrum, it's still not well resolved, and we need to go into very small current numbers which are not necessary for the MHD equation. So therefore, if we want to actually solve the gravitational wave equation in this way, then this would require to solve the full system of MHD and gravitational waves with a very small time resolution, which is very, very inefficient. So we abandoned this idea. Well, I mean, it's still in the pencil code as this special module gravitational waves HIJ, but we're not using that anymore. What we're using is what is called gravitational waves _ HTXK, and okay, what is a slightly different approach. So what we're using is we are considering the gravitational wave equation. Already, we are discretizing the source for every time step that we are using for the MHD equations, And during one iteration of time, we are considering that the source term is constant in time. And therefore, we can solve for the gravitational wave equation completely analytically between time steps. So, and this is what with Axel and Ramkishore and Newton we were planning to discuss now by the second part of this session. We wanted to discuss what is how accurate is this and what it's scaling with delta t, because this seems to just be considering a constant term. So this in principle should be the error on this solution should be actually proportional to delta t, which is not what we have in the rest of the pencil code, and not actually what in the end we want for further results in the case that this is what is happening. So Axel did some numerical tests for this, and I'll now go into some generic results, and then we can come back to this discussion if at the end or at any time. So if you please feel free also to interrupt me if you want to discuss something regarding this topic. So this is also something that would be affecting, for example, if we have inflationary magnetogenesis, because we're so what Axel and Ramkishore are using is a slightly similar approach to this one. Is so when you have an inflationary magnetogenesis scenario, you're solving for the magnetic vector potential, which is here scaled with factor of f, a similar equation to a wave equation as well. It's a wave equation, and in fact, I think you can correct me if I'm wrong, that that they are adding a damping term which is proportional to the conductivity, and therefore this can be this is actually slightly modifying the dispersion relation that we had in this case. So omega in this case is lambda, and delta eta would correspond to the delta of like the time step in conformal time. So a similar approach to before can be done to adapt the fact that we have an additional damping term, and therefore it becomes a slightly more complex, this rotation matrix, which in the previous case was just the cosine and sine functions, but still it can be done analytically to obtain the solution by assuming that this is constant in time, and then we can just discretize in time and get this solution within the pencil code. But yeah, I mean, in this case, there is no sourcing, but if you have some sourcing, then it's this sourcing what you're considering constant in time. So this is the approach that is being taken at the moment within the pencil code. So therefore, it's important to understand what is the impact on the final solutions with of this assumption. Therefore, the scaling of the error of the solution with the time step. So actually, okay, I will now present some of the results that have been obtained in the last years with the pencil codes, and then at the end we can then go back to this discussion or to any other discussions that you might be interested in. So we can consider, and this is now for phase transitions, magnetic fields. So we can consider either that the magnetic field is already present initially, and then we compute the MHD evolution of these magnetic fields and the production of gravitational waves. And everything that I'm saying is also applicable to considering an initial velocity field, but I will be just focusing on magnetic fields here. So as I was presenting yesterday was for the non-helical fields, but now if we want to consider also partially helical fields, then we can add this sigma parameter into the expression for the magnetic field spectrum, where sigma is controlling the amount of helicity in the initial conditions of the magnetic fields. And when sigma is equal to 0, we recover the non-helical case. When sigma is equal to plus or minus 1, then we have fully helical magnetic fields, with again a developed turbulent spectrum, which k proportional to 4 in the at lower wave numbers, and k proportional to minus 5/3 at high wave numbers. And at the moment we're using this d equals 0, but recently I adapted that and I need to include that in the pencil code actually for this d to be slightly different. And when this D is different, we can adapt that the position of the peak, of the spectral peak and its value are actually this EM star and K star. But at the moment, this D is equal to 0 in the code. So therefore, this would be like a smooth broken power loss I was presenting yesterday. And we have like different parameters depending if we want to study the electroweak phase transition. Then we're considering that the energy scale, the initial time is around 100 giga-electron volts. And if we want to study the QSD phase transition, then we consider the initial temperature scale is around 150 mega-electron volts. And then we can consider different values of the parameters of the spectral peak of this magnetic field, as well as of the total energy density that's going into this magnetic field. And these will, in the end, be functions of it will be determined by the specific magnetogenesis scenario that one wants to consider. And then we can connect the different magnetogenesis scenarios with the potential observations of gravitational waves due to these primordial magnetic fields and their development of emitted turbulence. So yeah, just as an example of this type of initial conditions. So then this is what I was showing. So this is proportional to k to the fourth power and then to Kolmogorov with some smoothing around the peak. And then when we obtained this is one of the very well from 2019 paper already. So initially we obtained that the solution of gravitational waves for such an initial magnetic field, which is completely given, had a spectrum which is approximately constant and then falls as k to the minus 11 thirds in terms of, so note that I'm sorry for the different conventions. So here I'm dividing omega by k. So in the results I was presenting yesterday, I was presenting omega, and now I will quickly show those results again. So in that case, this would be proportional to k instead of flat, and then will decay. So this we obtained initially for these values of the parameters. So when the wave number, the spectral peak is around 100th of the size of the Hubble horizon at the time of generation, and when the total energy density of the magnetic fields is around the 1% of the total energy density, of the total critical energy density of the universe at that moment of generation. So this was a very an interesting result that was not initially thought from analytical point of view from the theory, and that we obtained from the numerical simulations. And further, in the results that I was presenting yesterday, we actually find the development of this k to the cube in this case. Sorry, in this with this normalization, since we're dividing by k, would correspond to this k squared that I was referring to here. And then we obtain something that is slightly proportional to k, which is again corresponds to this flat part, and then the decaying part, which is again the same. So in this case, there is no differences. So with further numerical simulations, we were able to find this for now. The k star parameter is slightly smaller, so it's at 2 pi instead of at 100 times 2 pi. It's still not clear what happens when we have larger wave numbers, but this is things that are being studied at the moment. And and I was showing yesterday some analytical model that actually helps understanding this type of spectrum. But what I wanted to show here is that in general, we find that this gravitational wave spectrum, its value at the peak is proportional to the square of the energy density of the magnetic field and inversely proportional to the k star, which is what we also obtained in these simulations and some other simulations. So regarding detectability of these signals, as I was saying, if we apply this to the electrowave phase transition, it was what we initially studied, then these signals might be detectable by LISA. And here I'm comparing, so these were all results from the simulations. This in brown is actually the analytical model adapted to these specific scenarios, so then it still works well. And in black is the case with almost non-helical magnetic fields, while in red is with fully helical. And this analytical model has only been developed for non-helical, and we're actually currently working on adapting that to fully helical. In the case where we have an initial magnetic field, we slightly observe any differences. The spectral shapes are very similar, but that is not the case in general, as I will be showing now in a moment. So we can use these to study the potential detectability by electrowave phase at the electrowave phase transition by LISA, and we can also study the potential detectability by pulsar timing arrays of such gravitational wave spectrum with pulsar timing arrays. So this is some interesting science that we have been doing. But one of the main disadvantages of the model I was presenting so far is that we're considering that the magnetic field is initially present at the initial time of the simulation. And we know that that is not very realistically. And what we actually could expect is that there is some magnetogenesis production. So the specific dynamics of the magnetic field during its production will actually be affecting what is the final spectral shape of the stochastic gravitational wave background. So in the case of phase transitions, this is still not very clear. So what we initially did was to add an electromotive force into the induction equation, where we're injecting energy at some specific wave number with some specific amplitude in order to then after some time, then this will develop the fully turbulent spectrum for the magnetic field. Then this will decay as I was explaining earlier. And during its early initial times of the magnetic field evolution, this will be actually leading to the generation of gravitational waves. So in the cases where we're considering where there is an inflationary magnetic field, this is already taken into account by the Maxwell equations in vacuum, because this is actually leading the dynamical evolution of the magnetic field from its generation, and therefore in that case we don't need to include such a term. And in the case, for example, that Jennifer, Axel, Yutong, and Matthias have been studying for the chiral magnetic effect, again, the chiral magnetic effect would be actually leading to this generation of magnetic fields. And that can be seen because in that case, this electromotive force would be the additional current density that we have due to the chiral magnetic effect. And therefore, in that case, there is also not this kind of ad hoc addition of an electromotive force in order to model this magnetogenesis. So the case of inflation, the case with chiral magnetic effect are naturally giving a magnetic field that is already being produced, and its dynamical evolution is already taken into account in the tensile code. However, from phase transitions, the situation is not as clear. And also for other types of magnetogenesis scenarios, the situation is not completely clear, and it's not completely known what are the actual dynamics that are leading to these magnetic fields. So the attempt that is at the moment being done is to include this electromotive force, which again, we can include the sigma parameter to have fractionally helical fields. And some results for this, well, this is just the magnetic field. We start with a quasi-monochromatic forcing at some energy injection scale, and then this develops after a few times the Bachelor spectrum, K4, and then the Kolmogorov spectrum. If we leave this for later times, it will fully develop the gravitational spectrum. The magnetic turbulent spectrum. This has some implications on the final spectrum of gravitational waves. So here I'm showing what we had before for the case where we starting with an initial magnetic field, and these red and black lines correspond to the black line is a non-helical field, a non-helical forcing, and the red line is a fully helical forcing. And therefore we see slight differences. So more or less the scaling is slightly shallower, but it's approximately constant. However, in the inertial range, there is a much steeper decrease of the gravitational wave energy density with frequencies. So these are important aspects that we need to understand better in order to have an accurate prediction of what is the stochastic gravitational wave background produced by MHD turbulence. Here is a comparison with acoustic turbulence, which is in general more efficient, and this is also something that we have tried to understand better, but it's not completely clear. But in this case, as I said, I'm focusing mostly on magnetic fields. This would be if we have a hydrodynamic acoustic turbulence, which is expected.
May I quickly ask?
Yeah.
So the magnetic field that you generate in the two different forcings, the RMS value is exactly the same that you generate there, or?
Yes, I mean you can adapt the amplitude of this magnetic field such that once that you stop. So yeah, I didn't explain that, but this electromotive force, what we do is we usually consider that to be present for a short amount of time or a specific amount of time, and then we switch that off. And at the moment where we switch that off, then the magnetic field starts to decay. So what we want is to use this forcing amplitude such that the amplitude at that moment is the same as the one we want to compare with otherwise.
Okay, thank you.
Yeah, so therefore there are slightly differences and we need to understand this better. This is, for example, a paper by Axel with some other collaborators where they studied this for nanograph when the nanograph results came out. And in this case, they're also using driven forcing for the initial times. And again, we see the drop of gravitational wave energy density and then much steeper slopes in the inertial range, as well as slightly modified slopes in the subinertial range, although more or less similar. In the previous case was proportional to F. In this case, proportional to F to the 1/2. Here is more. Here it is indeed proportional to F, depending on the specific conditions of the turbulence. So just I'm about to get over. So in regarding the efficiency, what we observed is that when we have an initial magnetic field, so this could be seen here, for example, besides the different spectral shape, there's also a decrease in the total gravitational wave energy density for the same amount of magnetic energy density, what Jennifer was asking. So like if we compare for the same amount of magnetic energy density and when the magnetic field starts to decay, and for the same energy injection scale, because that would also affect the production of gravitational waves, then we can study what is the efficiency. So here we're compensating by K star and by omega m squared. And we see that for the case with an initial magnetic field, so this is the evolution with time, but in the end we'll have just something that stabilizes after an initial production phase. So with the case with the initial field, we see that this is smaller than with the case where we have a forcing duration. In this case is a short, so approximately, I think this is 10% of 1 Hubble time. In this case is I think in this case is 2 times Hubble time. So therefore, if we have a short forcing, then there is a slightly increase in the gravitational wave energy density. And if we have longer, then we have a slightly even more increase, and this actually saturates. So I think that even if you run long, if you include the forcing term for longer, then after some point, this is not increasing much more. And in the case of acoustic turbulence, again, this is much more efficient for the same amount of kinetic energy density and the same wave number of the injection scale. So in the case of inflationary magnetogenesis, the setup of the simulations are slightly different. So there is some, in that case, you have the full Maxwell equations. So you're solving Maxwell equations in vacuum, and you give an initial spectrum for the magnetic and the electric fields. In the case where we're in radiation-dominated era, we're assuming the conductivity is so large that we only have a magnetic field. And therefore, with these initial conditions, so in these papers by Rankishore, Axel, and Newton, they started the production of gravitational waves. And hence, so showing for different end-of reheating temperatures, you might have a gravitational wave background that will be peaking and appearing in different in different parts of the spectrum, so different frequencies. So this could, in principle, be potentially probed by LISA. Actually, yes. So this is from a paper with Yutong and Axel, where we're actually studying these nonlinearities and its effects. So here I think is very similar results from this previous case, because we're also considering inflationary. And these are the runs, the solutions for the linear solution of gravitational waves, these green, red, orange, blue, and purple lines. And the first order nonlinear term that we studied produces an actually much smaller gravitational waves. So we see here that at least in this case, it's not relevant to take into account this nonlinear term, at least for the energy density. I don't have time, but it has more interesting aspects in the polarization of these gravitational wave backgrounds, but that I don't have time now to explain. But yeah, as you can see, depending on what is the end of reheating temperature, this might be detectable by pulsar timing arrays, as well as some astrometry methods that have been proposed. And in the case where the end of reheating temperature is much larger, then you might have something detectable by LISA, for example. So this is again a comparison of this is the case where we have an initial magnetic fields produced, the case where we have a driven magnetic fields. So again, like the gravitational wave is enhanced, production is enhanced, and there is a much steeper slope after a drop around the peak. And this would be the spectrum from this inflationary magnetogenesis scenario for a helical and non-helical field. So this have to be studied and understood in more detail. And here I am. So again, when we have chiral magnetic effect, and this, I think that Jennifer and Axel will be able to explain this better than myself. But we again find that there is a slightly differences in the spectral slopes of the gravitational wave spectrum. So what I want to highlight is that there have been different ways to study this, and the final spectrum depends on what are these initial conditions and what are the physics driving the magnetic field or the velocity fields. And we need to in the end, to have a way to understand the different scenarios and to relate what is the spectral shape that we're expecting in the end from the different scenarios, and to understand why these different scenarios are occurring and what is that is driving to these different spectral shapes of the stochastic gravitational wave background. So with this, I want to end, and sorry, I took a bit too much time, so I hope we can still do some discussion. I just want to mention some work in progress. So I have been putting some post-processing routines on like the results from some of the work in which I have collaborated on GitHub. Actually, this might be of your interest. There's also some interferometry and different cosmology Python routines that are I think of interest for gravitational wave calculations. And I'm trying to unify all these results that I have been showing, not only by me, but also by other people in the Pencil code within this GitHub, using the data sets that are in general made public. So I think it's good to have like a kind of a unified framework to understand the different scenarios, and some things that are of interest or currently being worked is to understand more the analytical evolution of the gravitational wave and how it's production, and that might be done using the unequal time correlators of the turbulence for the gravitational wave production. It's also of interest to try to extend the MHD equations into a highly relativistic regime, which is at the moment not possible, and we were justifying that because the total magnetic energy density has to be below 10% of the critical energy density according to Big Bang nucleosynthesis limits. However, this has been recently revisited by Tina Kaczynashvili with Axel and some other collaborators. And it seems that this limit is not as strict, so we can actually go to much larger magnetic energy densities, and that implies that we can go to larger Alfvén speeds that can become close to the speed of light, and therefore we would actually need to extend those MHD equations into the relativistic MHD if we want to study that in detail. And yeah, some other work in progress I was showing is nonlinearities in the gravitational wave equation, as well as modified gravity. And yeah, and that's it. So yeah, thank you very much. And maybe we can now start the discussion in the last 15 minutes. And
yeah. Thanks, Alberto, for such a detailed and exhaustive talk. Now it is open for the questions. If anybody wants to have some comments, ask a question, they can just ask.
Maybe I have a question. These nonlinear terms that you implemented, you showed some results earlier in one of the plots. Yeah, here. So this is just a nonlinear contribution as this dash dotted line, or this is just a contribution from the nonlinear term. It's not the absolute result that you get.
Yes, it's actually, so the solid line would be both terms, like linear plus the first order nonlinear, and this would be the nonlinear. So it's just to compare what in several orders of magnitude smaller.
Right.
So in terms of the energy density, it's not too relevant to take that into account.
But you mentioned it's more relevant for the polarization.
Yes,
Comment on
yes.
that? Or do you
Yes.
have?
So I don't have any plots here, but I can maybe then send you some plots. Yeah, definitely. I can show you the polarization and how that is actually affected by this addition of the nonlinear term. So we see some. Yeah, I decided to take out any discussion about polarization since I was already taking quite some time. But when you have your spectrum of polarization, and we have seen that when you add this nonlinear term, there is some drop after some specific wave numbers, depending on how strong is the turbulent sourcing. So therefore, in that sense, we think that it's interesting to consider that.
Okay.
Matthias, yes, you can ask.
Yes. Hi, Alberto.
Hi, Matthias.
Thank you for your talk. I have a sort of an elementary question. So, given that the gravitational waves are carrying energy, they need to drain energy from somewhere. So finally, there must be a back reaction of the gravitational wave on the sources. So that might be completely negligible, but could you comment about that? In terms in the context you are doing these investigations. So early universe.
Yeah, so as you're saying, I mean, okay. So what we're considering is that the metric tensor is that given by an isotropic and homogeneous universe plus these trains, which is then what we're solving for, right? And so this back reaction problem would appear if, well, not problem, sorry, this back reaction would appear in the metric tensor that we're using in order to obtain the MHD equations, right? Because now we're just obtaining these equations in just using the metric tensor. This so in general for gravitational waves, and also what we observe is that these are much smaller, and that's actually one of the conditions for these to be gravitational waves, that these strains are much smaller than the values of the background metric. So therefore, this contribution it's negligible, but also you could say then, okay, how negligible is that? Let's try to implement that, but this becomes very complicated because in that case you have to solve for the full GR-MHD system. So you have to then solve for the MHD coupled to the Einstein linearized field equations, which then becomes it adds a very big complication.
Yeah. Yeah, that was what I expected.
Yeah,
thanks.
Sorry.
Yeah, go on.
I can also add a part to this. Basically, like, I mean, the energy is coming from only from, let's say, if it is dominated by the magnetic contribution, then magnetic energy will be converting to gravitational waves. So just to give, and both are like, since magnetic energy, like this is a decaying turbulence setup. So magnetic energy is also going down, and the efficiency of creating gravitational wave will also be reduced with time. So if I give you some numbers, let's say you take an example, when the magnetic energy initially is like 10%, and when both are get saturated, the gravitational wave will be roughly 1%. And compared to the total energy budget. So the back reaction of the gravitational wave on the magnetic field evolution will be negligible. Yes.
Yeah.
Yes, and if I can add something, so and indeed, as Gravitational is explaining, when you have the production of gravitational waves, there's energy going in from magnetic field into the gravitational wave, and this will be negligible. And in this case, we are not taking that into account, because then you would need to put the back reaction here. So we won't be seeing the effect of this decrease of the magnetic field, but it should, in principle, be there. But again, like that should be negligible.
Yeah, thanks.
If there are any more questions, you can ask.
Maybe answer the question.
Yeah.
I have a question, but it's actually very naive. So you at some point you showed this equation for gravitational wave, this Hij or something like that, right? So then I missed how that feeds into the MHD equations you later showed.
So at the moment, this equation it's taking the stress energy tensor as the source for the strains. So there is, and this is what Matthias was asking. So there is no back reaction. So there is no effect of these gravitational waves into the MHD equation. So MHD are solved separately. And when you compute the MHD equations at each time step, you can get the value of the stress energy tensor, which is what it's shown here, which has contributions from velocity fields and contributions from magnetic fields. So you solve for MHD equations, you compute for velocity and magnetic fields. Then you have to take the traces and transverse projection of that tensor and to take into account the gauge invariance of the strains. And then that is what you're sourcing in the gravitational wave equation.
So when you say GW turbulence, you're actually generating some power spectrum for this HIJ. That is that what is the GW turbulence?
Yes, so precisely if you have linear GR, the only turbulence that comes into gravitational wave has to come from the source, because this is a linear equation otherwise. So the gravitational the turbulence in the gravitational waves that we observe, it comes purely from the turbulence that we have in velocity and magnetic fields.
Okay, I see. Yeah. Yeah, thanks.
Mm-hmm.
Yeah.